So good morning and welcome to everyone. Welcome to this last webinar of the EU-SysFlex project. Today we're going to share with you the results of all the demonstrations that were led in work package 6, 7 and 8. Some demonstrations were also done in work package 9 on data exchange, but there was a previous webinar on that. So now we're going to focus on those last 3 work packages. Next slide, please. Quickly, so take you through the agenda. So first, of course, this short introduction of the project. I will lead you through a brief summary of the projects. Then we will discuss and present the results of the demonstrations that were led on the enhancement of the coordination between TSO and DSO to access flexibilities in the distributed system. Then there will be the results and the presentations of the demonstrations that were done on the virtual power plants in the projects, and finally a conclusion. So just I would like to thank very much for their work and thank in advance for their presentations. So in the TSO demonstrations, the German demonstration will be presented by Mike Stotz from Mitnetzstrom and Sebastian van den Berg from Fraunhofer. Then we will have the presentation of the Italian demonstration by Simone Tegas and Carla Marino from e-Distribuzione. Then José Villar from INESC and Susete Albuquerque from IREDES will present the Portuguese Flex Hub. Yeah, I was going a bit quick, so maybe you didn't have time, all of you, to say hello, but you will turn on your cameras when you will speak. Then we'll have an overview of what was done with PSC and the Polish real-time dispatcher training simulator. Then for the VPP demonstrations, the French demonstration will be presented by Yi Wang from EDF. Afterwards, the Portuguese VPP will be presented by Miguel Jorge Marques from EDP and Michael Wenzel from Siemens. The Finnish demonstration will be presented by Oliver Ojala for Helen. And finally, John Wallace from HairGrid will provide a view of the Irish qualification trial process. So I propose now that we start with this presentation. So I will, in five minutes, present the main outcomes of the EU-SysFlex project. Maybe some of you have already participated in last week's webinar, when we went through them and presented them, and especially the roadmap. But for a brief overview, so next slide, please. So the EU-SysFlex project, as you probably know, was a little bit more actually than the 4 years marathon that we are trying to successfully achieve now. This webinar is entirely part of the process. So in this project, we identified scenarios and the needs for the transition to cleaner low-carbon energy in the power system. Then we analyzed with a lot of comprehensive simulations what would be the needs for the system in terms of balancing, congestion management and stability when a lot of variable generation increases in the mix, the power mix. Then what sorts of solutions we can activate to mitigate those scarcities appearing to operate the power system. So, of course, at the core, and what we will present today, the demonstrations of technical solutions and processes that can help provide mitigations to these technical scarcities, but also the whole environment, from the economics, the data management, the market design, that can help and make these solutions appear and be sustainable in the future power system. And all these results were finally encompassed in a roadmap for the future. So next slide, please. So to focus on the demonstrations that will be presented, as I was saying, today in the webinar, the project was at the core of it was based, let's say, on solutions that were tested in the four work packages: work package 6 led by E.ON, work package 7 by a new EDP, work package 8 by EDF, and work package 9 by Ellering on the data management. So there were all industrial scale demonstrations, 3 demonstrations that were between work package 6 and work package 7 on how to access flexibilities that were mainly embedded in the distribution system. So how to operate that from a DSO perspective to deliver services that could help the TSO and the DSO, the needs of the future. So the main focus of it was the fact that we need critically, and it's a key to access those distributed flexibilities, to have a enhanced coordination between TSOs and DSOs, so across the different system operators. And then the other 3 demonstrations, the VPPs, between the French, Finnish, and Portuguese VPPs, to show how the value can be enhanced and how the services could be enhanced when, instead of just providing some services from smaller generation, we would aggregate, not only generation, but also other assets such as storage, but also demand-side response. And in an aggregated way, we could provide more services and more value to the system. And finally, as I was mentioning, it will not be presented today because there is a webinar and the results are still on the EU-SysFlex website if we want to see the replay of this webinar, the demos in Work Package 9 on enhanced data exchange to favor the access of flexibilities, especially across borders and across sectors. So next slide, please. The other results of the project, and I think it's worth mentioning today, is in the demonstrations, we showcased some solutions to provide the flexibilities, but it was an important part of the work to have a double approach, not only this bottom-up approach from the demonstration, but also a top-down approach, and see what would be the needs of the future. So this was done mainly in simulations, by developing several scenarios for the future and seeing what the scarcities would be for the system. And you can see here some extracts of the tables and the work that were carried out in Work Package 2 to show how some issues were raising in terms of inertia, so less inertia, in terms of frequency containment, but also in terms of voltage stability, in terms of rotor angle stability, and in terms of system congestion as well. So the fact that we did this top-down analysis was a great help to sort of help developing what types of services the demonstrations were supposed to provide to the system, what would be the needs of the system. Next slide, please. And as I was saying, to implement all those levers, to implement all those solutions, several levers are necessary to make both approaches. So bottom up with essentially the demonstrations, and top down from the needs of the system at European system level. Different levers are necessary to be activated. So namely, in terms of investment signals, that would be required very clear long-term investment signals to make sure that we develop the low carbon and flexible assets that will be necessary in the future. To also, and we will have an overview as well today, because I mentioned, of course, Work Package 6, 7, and 8, but there are also some information coming from Work Package 4 in terms of implementation in system operators tools, and this view will be provided by PSC and by AirGrid. The enhanced system services, so the new services and new players that will need to be in the market in the future, and the enhancements of the market design, and that will be necessary to make sure that those future services happen and are delivered in the future. And finally, last but not least, all the data management aspects that will be required and hugely required, as we see now a lot of resources decentralized and smaller in size, but in a much higher volume develop in the system. So not only in terms of generation, but also in terms of potentially demand side players, storage, etc. Next slide, please. And here is the summary of all those key outcomes that we have tried to summarize it in the flexibility roadmap. So just to go through it. So as I was saying, significant technical scarcities appear in the system with high levels of variable generation. Enhanced system services flexibility capabilities will be required to mitigate those. This required flexibility is not guaranteed today by existing market structures. So new flexibility products and market evolution will be required. Enhanced forecasting, state estimation, and optimization capability are necessary to make this happen. Efficient coordination between TSOs and DSOs is key, critical. Aggregation of decentralized resources will enable access to a wider range of flexibility options. And finally, a customer-centric approach with standardized access to data is crucial for effective data exchange. And without waiting, I will give the floor to Mike, who will present the first of those demonstrations for Germany in the TSO-DSO demonstrations. Thank you.
Yeah, welcome. So for the German demonstration, it's starting the TSO-DSO coordination session. What did we do? What was our goal? We wanted to provide flexibility services, active reactive power from the high voltage 110 kV distribution grid to the extra high voltage transmission grid. And why was it important, or why is it important for us in our grid? As you can see in the map, it's the blue part, and in our grid we have nearly 10 gigawatt of installed renewables and some conventionals also, but the peak load is below 3.3 gigawatt. So the spread is really high, and therefore there are issues with congestion management, voltage violation issues, and so we use the high voltage grid, over 1,500 assets for our demonstration, and the partners were Fraunhofer University Kassel, where Sebastian is part of, and he will tell some insights, and also Inestec was part of our demo. Sebastian will also tell something about it. And our first step was we want to use these flexibilities for our grid, and therefore we set up a process. This process is schedule-based and starts a day ahead after the closing of the energy market, and we take all the information we have. So after the market, the generators know roughly their in-feed schedule, and we use this forecasts and obviously grid data in our grid, so the switching plan, so that we know the right topology. We put it into the developed tools, this data. It is calculated, do we have congestions, do we have voltage violations in the future, day ahead, and then updated process intraday. And if we have so, we identify what flexibility is best, and then activated call for activation. So tell the aggregator, the operator, the generation operator to activate it. And since we have underlying system operators, also distribution system operators, we also include their data, what they expect as power flow at the interface to us, and what flexibilities is available, and at the end, after our calculation, if it's not feasible in our grid or it's cheaper in the underlying grid, we ask them to activate the named flexibilities. And since it's TSO-DSO coordination, we also included then the TSO and gave the information the TSO needs. It was a discussion with the TSO, what information is important, how should it be formatted, this information, and then the TSO can do with interday, with a day ahead, start their own process, the European coordination process for congestion management, and then give us the information back if any flexibility is needed. And this whole, this simplified process, let's call it this, is also then updated in interday. It's the same information flow again, the same calculation, only the European coordination of the TSO is not involved. But the rest is the same, and therefore our goal was to be in time and that we meet this thing. And the goal was the calculation in our part is less than 15 minutes. High goal was 5 minutes, but let's see, maybe at the end I can talk, say something about it, or Sebastian will say how fast they were. You can be surprised who will say it. And then this as a process, and then what were the needs to meet this process. As I said, we need input data, and this data is key. So the forecast you need, and to elevate the deviations and so on. But at the end, we also developed a combined optimization of active and reactive power flows, flexibilities, and to support each other and maybe to gain some enhancements. And at the end, so this was built up, and I think now Sebastian will go into the details and tell you something about it.
Thank you, Mike. Yeah, as you said, so there were some challenges, and we had to do some new developments and refinement of already existence methodologies and developments, and then bring them to the application. And I will give you a short overview over a few aspects of this, mainly the forecast, the optimization, and the whole communication system, namely our demonstration system. And starting with the forecast. So why was forecast needed at all? You know, we need forecast in order to make everything in the grid operation plannable. So since we do not have some fixed schedules, forecast is not so easy to achieve, and but it's very crucial in order to detect possible congestions in beforehand, in order to plan some measures. And what we need is that when we have the forecast states for generation and consumption, we can estimate the grid states, and then we can compute the flexibilities. So yeah, as I just said, what did we forecast? It was the wind forecast and the PV forecast. We use mainly physical models, but also time series, and use artificial neural networks in order to train these models and updated them with online data directly from the Grid Control Center of Midnitz. More or less similar to the consumption forecast. It's more tricky because you do not have these physical models, you have not the exact information of the installed power and so on. So it's mainly time series training of artificial neural networks at the medium voltage busbar. And then we get a reasonable forecast of the consumption as well. And both together, we were able to compute complete grid states on them. But one of the key results was that we need, for these approaches, a time frame or this time span where we have the real data and the forecasted data, and then we need to calibrate our models. And after the calibration, it was very well possible with these machine learning approaches and physical models to reach sufficient accuracy of the forecast in order to compute the future grid states and compute flexibilities. And computing of flexibilities is the next big thing we had in the last 4 years. It's more or less optimization in several directions. And why was optimization needed? First, in order to detect congestion-free active and reactive power flexibility potential. Why is the congestion-free flexibility potential so important? Because in the old days, it was often the case that the TSO had a request, and the request was sent to the power plant, but it was not possible to estimate possible related congestions which occur to the change of certain generators. And this is what we did here. We computed this flexibility with respect to possible congestions in the distribution grid in order to provide flexibility potential for the transmission grid. And not only at one connection point, but also at several connection points. And you can see here, this is our optimization approach. As I said, this was active power flexibility, reactive power flexibilities, and loss minimization, and then set point realization, because when you have a potential at the grid connection point and you have a set point at the grid connection point, you need to deaggregate this set point to the individual power plants. The key results were that the optimization of active power with respect to reactive power, which is also very important, because if you lose the active power, you can also lose your reactive power and then run into some voltage problem, for example. And so this combination is needed for stable and secure operation. And the consideration of grid constraints like N-1 or some local optimizations at DERs is also very crucial for successful optimization. And you can see in the little picture, these are reactive and active power flexibility bands. So this is the bands for one or more concrete solutions. But when we want to know how is my P and Q potential in general with different combinations of P and Q and also at different grid connection points, the colleagues from Inerstech developed a PQ maps optimization tool in order to investigate, analyze, and visualize these PQ potentials. And so this is needed that the TSO becomes aware of the feasible TSO-DSO operation conditions so that the DSO can avoid penalties for exceeding operational limits at the grid connection points. And this approach was also needed because there is some crucial data exchange between TSO and DSO, and especially in Germany, where the border between TSO and DSO is at the 380, 400 kV to 110 kV grid connection. So here again, P and Q are optimized, correlated with each other, and it was the estimation of the feasible Q operating points at the TSO-DSO interfaces through exploitation of the flexibility available at the distribution site, again from the different DERs installed there. And also the was estimated how the PQ flows are redistributed through several DSO-DSO interfaces. So these not only one grid connection points, but it's 2 or more grid connection points. And then we have, of course, interferences between these 2 and more. And this needs to be considered and taken into respect into the optimization. So the key results were that the PQ max could be computed with 3 different approaches. and only having the knowledge of the distribution network, and then with the complete information of the transmission side and with an equivalent, because you do not have always all these different informations. And if you do not have information from the transmission network and you do not have some transmission equivalent, the PQ maps are not reliable because you do not have the feedback from the transmission grid. So the equivalent network, which was developed here and applied here, needs to capture the transmission grid operations in order to give reliable results. And in the little picture here, you can see how these results look like. You can also find these results in our deliverable 6.5 optimization tools and first applications for decentralized resources. So, give me a second. Wait. So after we have some internal functionalities, you need to connect these functionalities, you need to import external data, and you need to have some communication with the user and the system. So this is why we have communication software infrastructure. And yeah, as I just said, you need communication between external data and internal functionalities, between system and the user, and also between the internal functionalities and methodologies themselves. We used a flexible, expandable modular architecture in order to cope with the new functionalities, because we need to be expandable, so we need to be flexible. We use for the communication between the modules a REST interface and a message broker, and we had a microservice architecture, which gives us the opportunity to add new functionalities and improve the current design. What we also found and out that this was very beneficial when we reduce the amount of different data models only to one real data model in our system. It's a SYN-CGMES, and if you want to go to power flows, we use the open source data model of PandaPower, so we can reduce the complexity of all the different data sources. These are also some of the key results. We saw again that SYN-CGMES is able to describe the data uniquely, and we had some delays due to communication via REST and message broker, which also, as Mike also hinted at, that we try to achieve to have the whole process faster than 15 minutes, also looking at the 5-minute limit. And this was one of the time delays we had into the whole process. Also, we found also the user interface is again a key for acceptance within the grid control center, because you need to really get the user to understand the program or the system, and that the user want to use the system. Yeah, so far from the development side, and Mike, you can present some of the results.
Then to sum it up, we talked about the flexibility, and here you can see the bandwidth, what is in the day ahead, forecast, prediction, optimization, however you want to call it. The red is active power, and the other color is reactive power flexibility. And here are some other results. On the left side, you can see if we compare the congestion management with the old scheme, we can have a lot of savings with our new approach. And on the right side, as Sebastian said, one goal was a reduction of grid losses. And as this is our yearly savings, or our yearly savings for supply of this energy is needed for grid losses. And as said, the time we met it, the complexity was reduced, information was all available at the end for the TSO, and high efficiency at the end. So that are the results of our demonstration. Thank you.
Thank you very much to both of you. We will move on to the presentation of the Italian demonstrations. We will take the questions. You can ask them in Slido, and we will take them at the end of this session. So please, I think, Simone, are you starting the presentation?
Thank you, Maria. Good morning, I'm Simone Tegas from Distribuzione, and in this presentation I will support it also by Carla Marino from Enel Global Infrastructure and Network, which is the linked third party of Distribuzione in this demonstrator, in which also RSE, Research on Energy System, worked with us in the implementation of our demonstrator. This demonstrator is focused on demonstrating how it is possible to provide flexibility services from resources connected to the distribution network, resources which can be owned by the DSO itself, but also by private owners. And in order to demonstrate it, we worked on a portion of a real distribution network characterized by a great amount of production from renewables, from distributed energy resources in general. A situation that can also cause backfeeding phenomena during the entire year. We worked on a portion of distribution network characterized in details by an installed their capacity of 39.8 megawatt peak with an average energy produced of 46 gigawatt hour per year. And in order to demonstrate the main scope of the project, we involved in our demonstrator different kind of flexibilities, starting from an electric storage system, including 4 photovoltaic generators, the load tap changer of both the transformer of the primary substation, which is the interface between the distribution network and the TSO grid, and we included also 2 STATCOM modules. And it is important to specify that we focused on, for the real field tests on reactive power, because our actual current regulatory framework doesn't allow to do the regulation of the active power. Next slide, please. We worked in order the different kinds of flexibilities in our test, and to reach the project goals, we set up a completely coordinated process for the ancillary service provision between the DSO SCADA and the TSO SCADA. All this process is based by the functioning of automated tools for network state analysis, network optimization, and reactive power management, developed and improved in some parts for the aim of the project. Naturally, because it's important to start from the network state analysis in order to understand the real state of the network, the real condition of the network, starting from the measurements coming from the fields and starting from the real state of the network, in order to process the network optimization and obtain the exact amount of capability range of reactive power we can make available to the TSO in order to receive from the TSO SCADA the request of specific set point to apply to our network in order to reach this kind of goal. And in order to improve the network optimization, we understood, we proved that it is important to improve the observation, the observability of the distribution network, together with an improved forecasting of res generation and load. In the next slide, you can see the entire chain, the entire architecture we developed for the Italian demonstration. It is based on two SCADA systems, a central SCADA which is able to manage and operate a wider portion of the real distribution network managed by e-distribuzione. This central SCADA is connected with a local SCADA, which is located in the primary substation of the demonstrator, and which includes the network calculation algorithm system, which is a group of tools able to start to do the network state analysis and the network optimization, which, according to the availability of all the flexibilities exploited in the demonstrator, and you can see them in the lower part of this slide, it is able to evaluate the capability range, in this case for the field tests of reactive power, and it is also and this range, it can be shared with the TSO SCADA according to the coordination, the connection between the local SCADA and the TSO SCADA. We need to underline that for the scope of the demonstrator, we needed to simulate the TSO SCADA because the Italian TSO is not a partner, a project partner. So we emulated this SCADA. We emulated the exchange of information between the local SCADA and the TSO SCADA, and in this part of the architecture, in this part of the chain, the TSO, the simulated TSO, can receive the capability range from the local SCADA, can choose a specific set point of reactive power included into this capability range, and send it to the local SCADA. Thanks to the implementation of a reactive power management tool, the local SCADA is able to split this reactive power set point to all the available flexibilities on field, and the local SCADA, the same local SCADA, thanks to the action of the remote terminal unit located into the primary substation called TPT 2020, and thanks to all the smart grids devices connected to the flexibilities, is able to apply these portions of set point to all the flexibility you see in the lower part of this slide. Starting from the next slide, you can see what happened in the real field test execution, and Carla Marino will explain to us what happened with them.
Thanks, Simone, for the introduction. So in these slides, we are going to show two of the main results obtained during real field test execution of the Italian demonstration. In particular, on the left side, there's an overview of the HMI SCADA located in the local SCADA in the primary substation of Quarto, in which the demo is implemented. In particular, in this picture, we can see that there's an inversion of the active power. So we are working in a day of the first week of February that is sunny, and we have the calculation of the reactive power capability that is shown in the upper part of the picture. So the Q min and the Q max that is possible, on which it is possible to, doing an evaluation in order to send a request from the simulated TSO to the SCADA. In the right part, it is possible to see an overview of the central SCADA, in which is possible to see the variation of the voltage on the bus bar of one transformer, the green transformer as the Enel convention. And so we have the shape of the voltage during the running of the test. The lowest value that is highlighted in blue in the picture of the voltage is about 15 kilovolts. This means that during the test, in which the automatic regulation from the integrated protection of the transformer shown in the previous picture by Simone act directly on the voltage, holding this level to a value of 15.4 kilovolts to 14.4 and 6 kilovolts. This is very important because make evidence of an increasing of the hosting capacity using this functionality, and also allow to see which is the effective variation also at the level of the PV generators, which contributes on the real field test. If we go in the next slide. Thanks. So we can see how the regulation has been activated also for the PV generators participating to the regulation. In particular, we can see a variation increasing of reactive power and also decreasing of the active power during the test for the group of Quarto FTB and the two groups of SANA 1 and 2, which regulated during the test the reactive power. It is important to specify that this measurement is averaged every 10 minutes, so it is possible to lose some significant point during the regulation, but during this time window it is possible to appreciate also a variation in terms of voltage. This voltage is, as you can see, is very well affected, and it's important to specify that the operated voltage of this kind of customer is very often very high. This means that there's the possibility to exploit this kind of functionality, considering that the operating voltage is very high, maybe with an optimization algorithm that is tuned like this one. We can study an alternative way to operate real network, medium voltage network with a lower voltage value. This may contribute to reduce the network losses, exploiting the algorithm developed by our RSC colleagues, but also to exploit this kind of functionality during the summer seasons, in which the contribution from the PV generators is higher. Maybe for the next question, we can wait for the question and answer, then I give another time the floor to Simone.
So we can go to, in these slides, we can see the main results, but I also explained them before because we needed to develop specific tools in order to reach the project goals. So you can go to the next slide. And these are the main feedbacks and lessons learned from our experience with the Italian demonstrator. First of all, the fact that smart grid solutions are crucial in order to improve the network operation and reach both the TSO and the SO needs. And not only a test from field, but also tests, real-time tests and offline tests in laboratory demonstrate that the flexibility share from different types of flexibility resources can provide different opportunities of regulation during the entire day. Naturally, in order to reach this goal, the DSO must optimize the distribution network, not only to reach its own scope, but also, as explained, to satisfy the requests coming from the TSO itself. We observed that in order to reach this goal, the process for flexibility selections and also flexibility provision shall be, as far as possible, automated. And in order to have a better service for this goal, for providing this goal, forecasting tool, optimization tool, and control logics together with a reliable communication system are crucial to enable the entire process. For us, it's all, and we are available to answer all your questions in the question and answer session.
Thank you very much to both of you. So please ask your question on the Slido, little S at the top of your screen, and we will ask them just after this presentation and the one from PSE afterwards of the Flexibility Hub. I will now give the floor to Jose.
Thank you very much, Marianne. Thank you, everybody, for attending this seminar. I will present the Flexibility Hub, which is one part of the Portuguese demonstration, together with my colleague from IREDES, Susanne Burkerke. Please, next slide. So the Flexibility Hub is a TSO-DSO coordination platform that has two main parts, which is one related with the short-term coordination and one related with the long-term coordination. Related to the short-term coordination, we have developed a local reactive power market that supplies reactive power to the DSO to balance its own grid, but also supplies reactive power to the TSO at the TSO-DSO connection point for the TSO reactive power needs. In the short term, we have also related with active power what we have called the traffic light qualification tool, which is a validation tool that allows to assess to what extent the activation of distributed flexibility in terms of active power can be made safely without violating DSO grid constraints. And for the long term, we have developed a grid dynamic equivalent model for the distribution grid to provide information for the TSO grid stability analysis related with this dynamic behavior of the distribution grid, especially related with voltage and frequency disturbances. So please, next slide. So let's focus first on the local reactive power. The idea for the local reactive power is to have a local flexibility market, as we have said. So in this local flexibility market, the resources, the flexible resources bid their reactive power availability, and these bids are used by the DSO to balance its own grid, but also by the DSO, which is in our approach, the market operator, also to provide flexibility to the TSO. And the way this coordination is done is by some, let's say, some kind of TSO-DSO agreement. So the TSO can have other sources of flexibility, of reactive power flexibility, but he communicates with the DSO by publishing its reactive power needs at the DSO-DSO connection point. It is based on optimal or on a clearing, on a technical clearing, which is based on a multi-temporal optimal power flow with overlapping sessions that take place each 15 minutes with delivery horizon of 7 hours to provide some flexibility to the resources to include the complex bits so as to allow, so for example, as to avoid excessive switching on and switching off, which, for example, can be useful to limit the operation of capacitor banks. So please, next slide. So here we can see where the physical demonstration took place, which is in the north of Portugal. The distribution grid of Frades, which is a high voltage distribution grid connected directly with with a TSO grid at one TSO-DSO connection point. And with several resources, we could consider flexible for the physical demonstrator because we have the capability of sending them set points, and other resources that were only considered flexible for the simulation point of view. And we have developed full reactive market platform, which is able to run in the real environment, receiving the bids from the real market agents. But in the simulation mode, we have also developed some market agents that are able to send the bids to the market and react considering the clearing results of this market. And the reason for using also a simulated environment is because several KPIs were really much better assessed by using this simulation environment, where we had much more flexibility to create different and more complex scenarios. So please, next slide. So here what we can see is just some print screens of the market platform. On the left, what we have is a small window, which is the log messages that is informing continuously on what it is going on the system, when the bids are received, when the market clearing takes place, and so on. Just close to this window, what we have is a timeline of the market, and this helps the people that is using the system to understand at which time where the process is. So we have the period where bids are being receiving, the clearing period, and so on. And on the right side, what we have is let's say the offline consultation or reporting tool that allows to select for any market session and to plot for each of the bids sent and for each of the resources, for each of the delivery times, what was the bid made, what was the price, what was cleared, and the set point sent to the resource, and so on. So please, next slide. So here we have two, let's say, communication architectures, one for the physical demonstration, which is on the left, and one for the online, for the offline or simulated demonstration. Just without entering into the details, just to say that for the online demonstration, we have three resources, but for the offline, we were able to consider also the other wind parks as flexible resources that were managed by an aggregator main function that was managing, let's say, these market agents to run continuously this simulation process. So please, next slide. Yeah, and the main difference between the online and the offline is the number of resources, but also the capability of having much more simulation scenarios in the offline demonstration. So for the offline demonstration, we were able to have different TSO-DSO reactive power profiles, different forecasted data, different flexible resources. We also could, let's say, change the network site to check for the scalability of the developed solution, and also even to relax, for example, the network operational constraint to see the impact on the reserves, on the reactive power flexibility available. So please go on. Next slide, please. Yeah, so here in this slide, this is just some screens showing some of the KPIs that were assessed. So for example, we looked at the bidding price for the reactive power. So we analyzed how what is the real cost of providing this reactive power, which in fact is mainly, when we talk about variable cost, is mainly related with the losses. So to assess the price of the bid, we try to put prices to these losses by looking at the energy price. So we developed several price scenarios considering these two factors. Then we have a look at the system cost of providing the service. And for this, we analyzed data from the TSO-DSO connection point related to the reactive power exchange. We made some clustering process. Then we identified some representative patterns. And with these representative patterns, we run the simulation to try to assess which could be the cost, both for the DSO and for the TSO, for the provision of this service, because we also develop a way to share these costs between both operators. We also looked at the increment of the available flexibility by considering the different scenarios. And some of them were, for example, adding new resources, and some were also relaxing, for example, the voltage limits, just to assess which could be the impact in the flexibility available. And finally, as I was saying, we duplicated the grid, and we looked with a different number of resources and different grid sizes to the computation times, with promising results, in the sense that we did not foresee significant problems related to this simulation time, considering also that what we developed is not a commercial platform. It was a platform for simulation, so probably a commercial platform would be optimized related to hours. And even in this, with this constraint, the execution times were really affordable for the resolution of the market session design. So please, next slide. So please, Suzanne, maybe you can comment this one, which is related with the physical demonstration.
In fact, in the Flex Hub, we did a real and physical demonstration with real assets. And as José told, this was an uncommercial platform, but where you can see logs, either from the distribution grids and also by other bids that were offered to the market in order to solve some constraints or some requests at the interconnected point. So, in summarize, the DSO sent the active and reactive power forecast to grid nodes in order to perform the power flows. Bids were received from, in this case, for our real demonstration, from Reactive and also by the EDP Renewables to solve some constraints. They were received by this platform. You can see here several logs. And then what basically it happens is that a simulation that it was performed by the algorithm of INESC solve what, in the point of view of market, was the bid that was successful. Then it communicates. We run ourselves at Reactive from our management tool, the plan, to combine all the power flows and clearances and to see if any violation could occur. Because we were doing this with real assets, in a real environment, and we were giving commands to the assets, and extra security was in place. So besides all this automation, we have an human eye that looked at our systems at the same time and gives the final okay to give the command to give this flexibility to the TSO at that interconnected point. I would like to emphasize that this is what was done in 15 minutes. So receiving the bids, giving the bids, and this double check from Reactive in order to give a flexibility at that interconnected point took place 15 minutes, and we could see the logs and who won the bids and the price, as Josette previously told us. So you can see the next slide. please, Marianne. Sorry. This is the logs, and this is basically what I was talking previously, that we run this in our tool, also the planning tool, because we are giving real commands. So we need to check that everything it was okay. We received the files. We'll check this on an automated way. But as you can, and before we give the connection, and you can see on the other side, on the other slide, we run also by the human eye aside if any violation was not detected in an automated way, and for the sake of the security of the grid, if it was okay, we gave that command. Everything in 15 minutes time. Thank you. José?
Yes, so I will give some additional information on the active power and dynamic model, but I won't go into so many details. Related with the provision of active power flexibility, here the way of coordinating TSO and DSO is simpler, I would say. So we assume that the TSO has its own markets, and distribution resources are able to send bits to this TSO market, and the coordination is based on the TSO trying to activate resources and bits that have resources located at the distribution grid. So it asks the DSO for a validation. The validation is such that if everything is okay, it provides the green light, and the amount of flexibility is the whole flexibility selected by the TSO. In case there is some kind of problem, there is a yellow light, and the DSO provides the amount of flexibility that can be safely activated. And finally, if there is no way to activate none of the flexibility selected by the TSO, then there is a red light which is provided to the TSO. So in this case, we did a similar analysis to those that were showed for the reactive power market, and as I was saying, we won't go into these details. So please, next slide. We developed a similar system. The physical demonstration was located in Évora grid, which is in the south of Portugal. This is not, in fact, a grid connected directly to the TSO, but the reason for this is that in Évora grid we had storage. And one of the features of the traffic light qualification system was the possibility of, by using this multi-temporal power flow, to include energy limited resources such as storage. So we developed also a similar full platform for this. Logically here we didn't simulate the TSO market, we just simulated that the TSO were asking for the activation of some of the bits sent. Please, next slide. Now, going to the third business use case, which is related to the long term. In this case, what we have developed is a dynamic model, a simplified equivalent dynamic model of the distribution grid. This was applied to Frade's distribution grid, the first one where we were developing the reactive power market. And the idea was to develop a very detailed model of the grid and to use this model to generate scenarios to train the simplified model. So the simplified model is really a model which has a very few number of components, but that are enough to reproduce reasonably the behavior, the dynamics of the distribution grid. So in this sense, the DSO can provide this relevant information for the TSO in terms of the dynamics of its grid without having to provide the full topology of the grid. So the process fits the parameters of the equivalent distribution grid model, and the result is this model that is provided to the TSO. This is done for voltage and frequency disturbances, and please, next slide. And what we could assess, which were the KPIs of this business model, is that the results of the dynamic equivalent model were really very good. And when compared to other let's say, more traditional approaches to provide this information, which is from the passive load to the IBG only or to the detailed one. Obviously, the detailed one is similar to the simplified one, and the simplified outperforms really significantly all the other approaches. And so let's go now to the last slide. Please, Suzette, you want to finish with this?
Yes, thank you. In summary, what we would like to stress is that DSOs and TSOs want basically the same thing, and that is the security of the electrical grid. And of course, the Flex Hub proves that if we coordinate our efforts, that can be achieved. Well, and this is very important if you take into account that we face the increase of intermittent rest at local level. And so it's very important that we establish this, and it is vital, this kind of coordinations. We also demonstrate that in a cost-effective way, we could do it securely and in a time that it was 15 minutes. So what this demonstration was really very important, because we could address that at the DSOs with the resources that has on its own grid, and if it has a request or a constraints at the interconnection level assigned stated by the TSO, we can mobilize and activate our resources at local level and give support to the TSO with avoiding any kind of eventual constraints that could happen if a blind command was given. So in terms, we did this demonstration, taking into account European guidelines and regulations, and also taking into account the ASEM report and ENSO and ETSO report. We exploit the flexibility of the resources by DSOs and TSOs for the short term. And we, as I stressed before, the coordinations between DSOs and TSOs were vital in order to respond in a timely manner, and we proved that we could do that. However, in terms of national regulations, there's still some steps to be pursued. Mainly markets that allow this technical validation by the relevant system operator, meaning that it's best that if we demonstrated that, knowing if the operator who knows its own grid, it's best, it's cost efficient, and it's more secure to mobilize its resource in order to resolve a constraints or a request at the interconnected point. We also saw that it was possible that we could mobilize, if we have some kind of constraints by the DSO side, we could mobilize other resources and still give that response. So in a technical, and I was kind of mixing regulatory and technical and economic aspects because they are also interconnected. Technically, we could see and prove that this was done correctly in 15 minutes time. Real activation were given by our assets, either what, like José said, by our batteries or other resources of the distribution grid, and also by the renewable side, and we solve those constraints. in terms of economical size, we proved that that could be cost efficient, and of course, this was, in my point of view, a good, very good project in this kind of times where European unions ask us to be to pursue our coordination schemes in order to be cost efficient, secure, and respond in a timely manner. So just to summarize all the hard work that was done and good work that was accomplished, we proved that DSO can adjust the DSO and TSO power flow to a value agreed with the TSO, and that could be done in a 15 minutes times, could be done safely, taking into considerations the restrictions of the distribution network, and this is very important, and avoiding blind activation in the distribution network without the DSO technical validation that could potentially cause harm. So we served the needs that were important in a coordinated way without avoiding constraints by any side. So I think it was a very good the project that allows us to prove that this is feasible. This is it was accomplished, and well, we are hoping that in the future, instead of one interconnected point, we could improve this kind of coordination. Thank you.
Thank you very much. We're a little bit late in the schedule, so I think we'll very quickly move on to Mateusz's presentation and provide the view of the RTDS. Just for the speakers, there are a few questions in the Slido, and we might not have time to take them in the Q&A, so if you can answer them directly in the Slido, it would be great and save us a little bit of time. So thank you, Mateusz. The floor is yours.
Good morning, everyone. Thank you for introducing me. So my name is Mateusz Skwarski, and I work as a research and development specialist in PSE Innowacje, which is a subsidiary research and development company for the Polish TSO, which is PSE, Polskie Sieci Elektroenergetyczne. Today, I would like to very briefly present to you the key outcomes of the dispatcher training simulator session, which have been focused on verifying in training the challenges for the flexibility in the enhanced TSO and DSO coordination. So maybe I will switch the camera off for the bandwidth issues. So the two-day DTS session, Dispatcher Training Simulator session, was organized on 17th and 18th of December 2020. So it was quite some time ago. Initially, we wanted to invite you to Warsaw to organize the physical meeting. Of course, due to the obvious reason, we had to organize it as a dedicated two-day webinar. So during those sessions, our training simulator has been used to present the training scenarios, which has been focused on introducing the new proposed services and new proposed dispatcher tools, which can augment the TSO-DSO coordination and help us to solve congestion management and balancing problems both in the TSO and DSO network. So the primary purpose of our dispatcher training simulator is the training of Polish TSO and DSO dispatchers, persons who operate in the control center staff and are responsible for operating the Polish power system in real time. So our RTDS is a dynamic simulator, which is based on the differential equations, and it allows us to observe physical phenomena with the time constant from a single hour to hundreds of milliseconds. So we can observe a lot of phenomena, including transient stability, frequency stability. Also, we are able to introduce long-term dynamics and voltage stability issues. The core of the simulator is the Aristo computational engine, which has been developed by Swedish TSO, Svenska Kraftnät. A PSC version of Aristo is deeply modified by PSC itself and we are using a custom-made external applications dedicated for the dispatchers, which extend the functionalities of the software. Yeah? Therefore, this enables us to present a virtual representation of the power system in order to train dispatchers who operate the Polish power system in real time. And in particular, the dispatchers during the sessions learn and practice how to operate the power system in states of disturbance, power imbalance, and even they are training the restoration procedures, which for obvious reason cannot be trained in practice on the real life system. Next slide, please. Thank you. So our dispatcher training simulator includes the following components, which is the computational engine. Of course, we have a dedicated SCADA replica, which is very accurate because we need to present to the dispatchers the same operational tools that they will be using in practice. As I mentioned, we have developed dedicated additional IT applications, which are the exact replica of the load frequency controller, which is used in the Polish power system. Also, we developed the power plant control application, also automatic voltage control for power plants and substations tools. We have tools for control of the PV generation, load, and also wind generation. And those three tools have been also developed for the purposes of the EU-SysFlex work package for demonstrations using the real-time dispatcher simulator. What are we able to do with the dispatcher training simulators? What the operator can do in this tool? We can change the network configuration by controlling the circuit breakers and disconnector. Also, we can control the tap changers. We can set the power operating points for generation units and also for the controls of the automatic voltage control and so on. Also, we are able to recreate the daily profile of the power demand for the groups of the load or even for the individual loads. This helps us to recreate the exact power system condition that happened or may happen at the specific time in the power system, and this is the very good basis for our training scenarios. So what we have done for the work package 4 to represent the future challenges for the dispatchers or the people who are responsible for the planning and operation of the power system. So next slide, please. Firstly, we have developed additional tools that can be used by the dispatcher during the training sessions. First thing was the inertia monitoring. We assume that inertia response is not a product of a system service for the Central Europe. We only consider inertia as a natural, non-controlled technical ability of the Polish power system. Yeah, because for the continental synchronous area, it's not needed to treat the system inertia as a specific system service due to the very broad interconnection for the whole Europe. Maybe for the smaller systems which operate in island mode, it is relevant. So we only developed a tool for the dispatchers that can help them to monitor the lack of the inertia in the power system and try to give them a signal when they need to activate the synthetic inertia or to start the synchronous generation to bring up the inertia level to the required values. So this tool has been used by the dispatcher to bring them information and to help them to operate during the training session. Next slide, please. So the most relevant IT tool that has been developed for the purposes of the SysFlex project was the congestion management and balancing services implementation. And due to the European guidelines and network codes, it will be relevant, or it even is now, for the transmission system operators to introduce a new type of the services that will help them to solve the congestion management problems, and even they can be used for the balancing problems as it has been presented in the training sessions. So we have proposed two products, which is the manual fast redispatching and manual normal redispatching, and those services are using the various resources which are connected to both TSO and DSO network, and these services are activated manually by the dispatchers. Yeah, you can see that the activation times are different for the specific types of services, and also the delivery time is also different. Next slide, please. What resources are we using to provide this flexibility to the grid? Of course, we are using the centrally dispatched synchronous generator modules, which is centrally dispatched generation units synchronously connected to the grid. These units will be managed by the current DTS Aristo tools that dispatchers are using for now. For the purposes of distributed resources, which are connected mostly to the DSO and also to the TSO grid, we have proposed this new type of IT tools that will help dispatchers to activate the flexibilities coming from the resources such as wind farms, energy storage systems, or even hydro or thermal units that are connected to the high voltage or extra high voltage grid, but are not classified as a centrally dispatched unit, and these units are not dispatchable by TSO using the central dispatchment system. So using those tools, we have proposed two different scenarios for 2 consecutive days of our training session. And in the next slide, we see the first day. We called it the summer day, and our goal was to represent the typical future day with high load demand, high ambient temperature, which leads to high solar generation. And also we faced a problem. We tried to reconstruct the problem of the solar eclipse. What will happen if we accidentally decrease the solar generation? And as I remember, it was reduction which led to loss of 1,000 megawatts of the generation. And we recreate this using the historical data from 2015. And could you click on this slide? Okay. And as you can see, we tried to simulate the solar eclipse, and it was a real challenge for the dispatchers. We've used our services to try to help the system, to try to balance the system. We also introduced some unplanned events in the extra high voltage and high voltage grid, also including the tripping of the synchronous connected centrally dispatched unit to make life harder for the dispatchers. And our dispatchers coordinate, our TSO dispatchers in coordination with the dispatchers from the high voltage grid solve the problems using the proposed system services, and used those assets which are coming from the distributed resources connected to the high voltage grid. And the second day that we have analyzed on the next slide, I will just briefly go through this. It was a winter day with very high generation of the wind power, very high export of electricity, and then we have faced several congestion management and also balancing problem, and we have tried to solve them using the battery energy storage system, which will operate using those system services that we have proposed. And also the result of the session was that we have managed to solve those problems and to demonstrate the real value which is coming from the flexibility connected to the DSO resources. So next slide. So we'll be coming to the final conclusions. So our dispatcher training sessions shown a significant value of the coordinated application of DSO connected flexibilities to solve both congestion management and balancing problems that have been caused by severe events in the grid. And also we have seen that according to those services, TSOs and DSOs should provide economic incentives to encourage service providers to locate the flexibility resources in areas which are the most effective to solve congestion problems. Because we have seen that sometimes we wanted to use the flexibility resources to solve some congestion problems, but there was non-flexibility assets that will help us to do so. So the main outcome of the dispatcher work was to work on the planning of the grid to locate those assets in the accurate areas. Also, the very important aspect of such training was demonstration how the interoperability between TSOs and DSO can help us to solve congestion problems both in extra high voltage and high voltage grid. Also, what we have observed that dispatchers need dedicated IT tools that will help them to automatically activate those products which are automated or semi-automated. Activate those products which are related with system services. The problem that has been mentioned by the dispatchers was that the amount of information and the actions that they need to perform to manually activate those assets was too large for the person. They said that we need a specific automation or artificial intelligence based tools that will help them to make decision. Of course, these tools still need to be human supervised, but only showing us possible option how we can operate. But they mentioned that it is relevant in the future development of the power system and how the dispatching will change in the future. So I see that we are quite a bit out of time. So that's all of the key messages that I wanted to share with you. If you want to ask any questions, please feel free to do it in the Slido. Thank you very much for the opportunity to present today and also to cooperate with you in the SysFlex project. Thank you very much.
Thank you so much, Matthias. Thank you. So I see, and you can see in the chat that the questions have been answered by the demonstration leaders. So as we're a bit late, we will move straight to the next presentation, please. Next slide. Yeah. So Ye, please, the floor is yours.
Okay, thank you, Marianne. So I will take the control of the presentation. I hope it works. Okay, great. So my name is Ye from EDF R&D. I'm a research engineer working there, and I will be pleased to give you an overview of the French demonstration within EU-SysFlex project. Okay, so a full-chain virtual power plant was proposed and set up in France by EDF and Anakin, based on innovative approach of what we call multi-services provision by multi-resources. The French VPP aggregates several distributed resources, including a 12 megawatt wind farm connected at the French distribution grid, which is 150 kilometers away from Paris, and other resources installed at EDF concept grid, which is a medium voltage testing laboratory in the south of Paris. There, 2 megawatt, 3 megawatt hour battery storage, as well as PV panels are installed. So the VPP's operational planning and control set points are generated by a centralized energy management system, or EMS, which was located at another EDF laboratory. To ensure a reliable data exchange between the distantly located assets and EMS, a dedicated VPP communication platform based on IEC 61850 has been set up for demonstration. Multi-service provision by the VPP has been demonstrated. Oh, sorry for that. Okay. So multi-service provision by the VPP has been demonstrated, including frequency support services such as faster frequency response, frequency containment, and restoration reserves, for which symmetrical products can be produced through a coordinated control of wind generation and storage. Flexibility solutions such as ramp rate control or peak shaving of renewable generation can also be provided by the VPP when the power system needs appear. In addition, the VPP can also trade energy in the spot market as an aggregator. So to operate such a VPP composed of variable generation and storage, several tools, including forecasting, optimization, control command, communication, and monitoring, have been developed, tested, and validated to ensure its full team management from a day ahead to real time. Besides all the operational tools which are necessary for the demonstration, we also developed an offline simulation platform which can simulate in realistic conditions the one second behavior of the whole VPP system from 1 day to several months. It was used to jointly tune the different software and to assess all the controllers before real implementation. It has also been largely used to evaluate the technical economic KPIs of the demonstration, which would require running the demonstration over weeks or even months without this advanced simulation platform. So more concretely, the EMS of the VPP comprises 2 layers. The operational planning scheduler provides optimal energy and multi-service schedules for the VPP every 30 minutes at most, based on the most recent forecasts and measurements available, and the short-term control, which is designed to manage the deviations and unexpected events within each scheduling time step, and sends more detailed set points every 5 seconds to each resource. In a simplified operational process, measures from each site are received every 5 seconds by the short-term control layer, and then necessary information for the planning scheduling is sent to the optimizer. And then based on the renewable generation forecasts and different market prices, as well as local measures, optimal set points are computed to position the VPP in both energy and services markets while respecting the technical constraints and market rules. As a main final step of the operational cycle, the short-term control sends the set points to each resource and adjusts them if needed. Note that at all times, signals sent by the system operators in case of emergency or grid constraints are always considered as priority set points for the VPP operation. One of the innovative aspects of the French VPP is to get involved in the crew management, the flexibilities and the services that can be technically provided by wind generation. Indeed, modern wind turbines can provide frequency services as conventional power plants, but in a different manner. These generators are designed to produce the maximum power that can be captured from the wind. So if they need to modulate their power according to the grid frequency, a dynamic curtailment of the generation should be first performed from the available active power, or the so-called AAP, which cannot be measured but only estimated in this case. Note that this AAP estimation is not a short-term wind power forecast and should be done on a per second basis for wind reserve constitution. We can therefore imagine that the quality of this estimation has a great impact on the performance of the wind reserve. Another point is that the provision of symmetric reserve by wind alone leads to important energy losses due to the generation curtailment. Therefore, a VPP composed of wind and storage could be one solution to prevent shortfalls, for example, by allocating only downward reserve on wind and upward reserve on storage. So in this slide, an illustrative example of our demonstration results is shown, which was extracted from the tests performed on October 22nd of last year. As a first step for operating the VPP, its day-ahead schedules were first generated with respect to the market prices and to the day-ahead forecasts. As you can see on the graphs, regarding the energy planning on the left, the battery was scheduled to be charged when the electricity prices were low and discharged when prices went higher in order to optimize the VPP revenue. A certain volume of FCR was also scheduled, as shown on the right graph, as FCR prices were quite interesting on the day of the test. To avoid costly and unnecessary wind curtailment, upward reserve was mainly allocated on the battery, and the downward reserve was allocated on the wind farm when it was available. The VPP energy schedule, as well as the allocation of FCR between the assets, could be re-optimized and updated through intraday rescheduling. In the meanwhile, the symmetry and the total amount of reserve declared on day -1 at the VPP level were always respected, as this is required by the current FCR market and by the grid code. So here on this slide, the real-time behavior of the VPP is shown. The actual power of the VPP corresponds to the sum of the battery storage power and the power output by wind and PV generators. As programmed by the operational planning scheduler, the battery followed the 30-minute set point defined by the optimizer and provided FCR around its baseline operating point. The wind farm also contributed to the frequency regulation as scheduled. We will have a zoom on the behavior of these assets afterwards. Then if we look at the PV generation, it was not directly controlled by the EMS for this demonstration and always output its maximum power. And on the bottom graph, both the ideal FCR response expected from the VPP and its actual response for the whole test day are illustrated and compared. So it can be observed that the actual response was quite close to the perfect frequency regulation with some occasional deviations, which reflected a good overall performance of the FCR service provided by the VPP. The deviations came mainly from the wind AEP estimation errors, as mentioned before, and also from forecasting errors, as FCR must be committed a day ahead in the current market design. If we took a look at the inside of the VPP, on the battery side, the total power corresponds to the sum of the baseline power for trading energy on spot market and the power dedicated to FCR provision. The control of the state of charge of the battery was not activated on that day. Therefore, differences can be observed between the actual final state of charge and the planned set point, especially during the period of extended frequency deviations. So if we take a further zoom on the behavior of the battery at around noon, it clearly shows that the battery only responded to under frequency events when upward reserve was scheduled to be provided by the battery. Then, if we took a look at the wind farm, its estimated available active power and the actual power output during the day are illustrated on this graph. When only downward reserve was provided, these two curves are quite close, and it seems not obvious to visualize the difference, as only frequency excursions much higher than 50 Hertz would make the wind farm reduce its generation from the AEP. However, during the hours when the wind farm provided upward FCR as scheduled at 7 a.m., at 10:30 and 2 p.m., for example, a power gap was constantly maintained between the AEP and the actual power for reserve constitution and for FCR delivery. So just to conclude, the concept of multi-service provision by multi-service has been successfully demonstrated by the French VPP. Although the illustrated examples given today were focused on the FCR service, many tests have also been performed to demonstrate the other services. It has been highlighted that the integration of a storage in the VPP increases the opportunity for wind generation's participation in the current FCR market and enhances the performance of the services provided. The provision of frequency containment reserve in addition to energy arbitrage helps increasing the VPP revenue, but also enables the VPP to effectively contribute to the resilience of the power system. In addition, the reliability and the performance of the reserve provided by the VPP has been demonstrated to be greatly dependent on the accuracy of the wind forecasts and on the estimation precision of the instantaneous available wind power. Due to time limitations, many detailed results cannot be fully shown here. For those who are interested by our work, they can have a look at Work Package 8 deliverables of EU-SysFlex project, which are published online on the project website. And a few words on the lessons learned and recommendations. So recommendations for improvement have been detailed in the final deliverable of the French demo. In terms of optimization approach, control command, communication, architecture, etc., without going through exhaustively all the aspects, I would like just to emphasize the following points. So first, regarding the capability of wind generation for providing frequency reserves, the estimation of the available active power is key to enable the services and to ensure their performance. Many works still need to be further done to enhance the accuracy of the AAP estimation. Regarding the VPP operation, a reliable, secured, and let's say standard-based communication system is of great importance. Through the French demo, it was also showcased that virtual power plants aggregating renewable generation and storage have a good technical potential for providing ancillary services. Their capabilities in fulfilling the flexibility needs of future power systems should therefore be carefully considered and better exploited. Okay, thank you.
Thank you very much, Ye. So if you have questions for Ye, please ask them on Slido, little S at the top of your screen. And we will now move on to the presentation of the Portuguese VPP by Miguel.
Hello, good morning. Good morning, everybody. Thanks a lot. Thanks a lot for the opportunity. Thanks for having me, and congrats to my fellow speakers today who have been showing their great work. So as Marianne presented, my name is Miguel Marques. I work for EDP, and I'm going to present to you the Portuguese virtual power plant demo, together with my colleague Michael Wenzel from Siemens Energy. We'll go, through the concept, explaining what is it, what it is, looking at the demonstrations we carried out, and wrapping up looking at the results obtained and the key conclusions, key takeaways that we got from the project. So in the next slide, sorry, maybe it's easier. Yeah, okay, thank you. Okay, the concept of the virtual power plant, as you are probably aware or familiar with, is this idea of aggregating different units under one single coordinated control. And this obviously becomes more interesting and more relevant once we have variable renewable units like wind farms, in the sense of there's a potential there to pool resources, which is what we did in the virtual power plant. So for our VPP, we are combining different units with fundamentally different natures and characteristics. What you see there is that we pick up a wind farm, which has obviously a variable output. What you see there in the picture, by the way, is this a daily generation profile of a wind farm, of an individual wind farm. So we pick this up and we combine this with a hydro plant, a very flexible one, that, as you will see, capable of varying its output within a few seconds or a few minutes to adapt to the variability of this wind farm. What we see there, what we do then is to combine both of this. Obviously, this is for illustration purposes, but what you see there is that the hydro has changed the output to match with the wind farm's output. In this case, I should say that for Portuguese VPP, we do not have any curtailment of the wind energy generated, so it's just an entry. We pick it up as it is, the wind farm output. We combine the two, and we have a unit that is self-balanced, in the sense that any imbalances that exist from the wind are compensated by the hydro plant. Now, this becomes interesting, of course, when the wind farms, at a point at which the wind farms will lose fixed income mechanisms, fixed revenue mechanisms, like feed-in tariffs, which is the case with a lot of plants worldwide, but specifically here in Portugal. As these units have to find ways to participate in energy markets, get remunerated, and manage their own imbalances. So in the next slide, we have an overview of, which I think falls in line with that let's go to the animations till the end, because the animations are a bit, and finally, thanks. So in line with what I was saying, we set up this Portuguese VPP as a way to increase the flexibility at the disposal of the operator, of these the types of units. In our case, we have hydro and wind. The concept of this utility scale, because it's utility scale VPP, slightly different from the traditional VPPs or the original VPPs. The concept for this is the segregation and the joint control and operation of a variable speed pump storage plant and 2 wind farms, as I'll show you in some more detail. The VPP is then, this tool to manage multi-technology generation portfolios, and also our plan is also to show how the wind farms can be integrated under a VPP to participate in reserve markets. And finally, we mainly want to explore this option and also push the boundaries a bit more. As of today, Portugal is still organized in different balancing areas, and this concept challenges quite significantly the status quo, the current state of affairs here, regulatory-wise, So here's on the right-hand side, you see the general configuration of the VPP. On the left, we see the generation units, which we'll discuss ahead. Some are in EDP Produção's portfolio. EDP Produção is the company of the business unit within EDP that owns and operates the so-called conventional assets, which includes hydro. A lot of it is hydro, most of it is hydro. And also other units are under EDP Renewables, which is EDP's renewables business unit. One important note is the fact that at one point we considered the option of expanding the concept to a hybrid setting that EDP Produção is also working on. This hybrid setting, which includes a hydro plant, a floating PV in the reservoir of the dam, and an electrochemical battery unit. We considered it. We started preparing for it, but at some point we understood that the timelines did not match, and so this is something that we'll probably do in the future work. On the right-hand side, you see the other actors in this configuration of VPP, the energy and the ancillary services markets, as well as the different data sources we need for the VPP to have all the data needed for its computations, which we'll get into some more detail as well. In the next slide, you see the assets that we've considered, the units that we've considered for the VPP, for the Portuguese VPP. The VPP was developed as this very versatile, flexible, technology-agnostic concept that will be easily adapted to different generation technologies. and different unit sizes as well. Of course, for our demo, we selected 2 units that made sense for the concept, in line with what I was saying with the premises that I defined previously, and also units that are of interest for EDP, in the sense that as the owner and operator of a varied portfolio of generation units, we understood that it made sense for us to bundle together these 2 units. So one is a very large variable speed pumped storage hydro plant, Venava 3, close to 800 megawatts of rated power, a highly flexible and very fast response unit, and 2, between commas, conventional wind farms, which total around 160 megawatt. These are the units. These are the units that we selected. They are geographically close to one another, to each other, because there's 3 units. But this did not need to be the case. I think I should highlight this also to explain that the concept can obviously be also developed and carried out in geographically distant units, provided that there are no constraints that prevent us from doing so. Technical, things like grid constraints, and also obviously regulatory, as is the case with the balancing areas I was telling you about. Either way, the concept still fits in well for geographically distant units. In the next slides, and I'm looking at the architectures of the deployed infrastructure. I will not go into a lot of detail. Michael will do that in a second, but I wanted to show you just the very high level of integration and the very transversal level of integration that we have of this deployment in EDP systems in both the corporate and processes networks. And it's transversal in the sense that we have integrated this procedure, this process, and the algorithms, and the way to send the set points to the units, all of this, and to collect data from the units, all of this across 3 different business units at EDP. They are all in the project. One is EDP Renewables, as I've mentioned previously. They contribute with the 2 wind farms. EDP Produção, as I said, they are the owners and operators of the hydro plants. And finally, EDP Unge as the EDP's trading units, so the company, the business units that participate with EDP's units in the energy markets. And I mean, this project, I think one important thing that we got from this project, which I would like to show, is that this project has allowed this integration, this link between different dispatches. What you see on the left-hand side are the different dispatches of EDP, which we find a very important takeaway of this project, a very important milestone that we achieved, because this paves the future for this hybrid future in which we have integration of across technologies. And finally, on my last slide, before I give the word to Michael, I just want to offer a slightly different perspective, if you can please. Yeah, it can go all the way through I can offer a slightly different perspective of the VPP, looking at the bidding with this VPP as an optimization problem, in which we take a lot of data, including the availability of the units, also weather forecasts, historical data, and we get the tool to generate the optimized bids. Obviously, the tool was developed by the consortium, by the colleagues at Siemens. We generate these optimized bids considering different time horizons in both the energy and the ancillary services markets, in which we're optimizing for the most scarce resource, which is the water available to generate in the hydro units. I mean, even more scarce as we speak right now, as we are currently going through this severe drought here in Portugal. And obviously we optimize to maximize the use of that resource. And so the VPP at the end of the day will provides a decision support tool. And part of what the VPP did, as you will hear from Michael as well, was indeed generating this, producing this suggested bids for the hydro plant operator, because again, the wind farm is not in a market and is still at the feed-in tariff. And so at the end of the day, the VPP is this complex, highly complex and multi-variable optimization problem. And I mean, and the way we got around to this project, to optimizing this. I think I leave the word to Siemens to explain with some more detail. So Michael, please, the floor is yours. Thank you.
Thanks, Miguel. Hello, everyone. Yeah, just to continue where Miguel left us, looking at what kind of tools we needed or developed as part of this project to operate and control our virtual power plant, is basically we divided the setup into two mainly different parts. On the left-hand side, we can see what we call the VPP core. This is the place where the optimization and forecasting is happening. Obviously, if we want to participate with the VPP containing wind farms, we would need to look at what is the available power from renewable energy sources that we can bid into the various markets mentioned already. We would also need to look at as in the end we are trying to come up with an economically most beneficial schedule for the VPP. We would need to look at energy market prices forecast, and these inputs feed into a complex optimization problem, resulting in two different things. One is the optimized market bids for day-ahead, intraday, and reserve markets, and then based on the accepted bids, we calculate optimized dispatch schedule in the simplified setup only for the pumped hydro storage, of course. As Miguel mentioned, we're going to take the wind as it is, but the platform is scalable to introduce different controllable generators as well. So this part of the tool is developed as a cloud service, so it's really running in cloud, and we were able to take advantage of all the scalability opportunities there. And on the other hand, we developed a tool which we call the VPP controller, very close installed to the automation level, to the dispatch center of EDP in the end. And this tool is taking the optimized power set points from the core and transferring these to the dispatch center of EDP, and also allowing us to collect data from the connected dispatch units. Okay, I can see we already jumped to the very last slide of the presentation. Should we skip the content in between?
No, apologies. Somebody just took the remote control from me.
Okay.
Please continue.
So can we jump back?
Yeah, can we back up? Yeah, a couple of slides. Yeah. Thank you.
Yeah, just around there. Thanks. So just going back to that infrastructure overview that Miguel showed, just to show you where these two components are located. So the VPP core as a cloud service, talking to a data provider on the EDP network that allows us to submit the market bids, and also to access the weather forecast that EDP provides to be incorporated into the optimization cycle. And on the other hand, the VPP controller on the bottom right part, located on a physical machine close to the dispatch center of EDP Unj. Okay, next slide, please. Yes, one more click, please. There we go. Okay, just to quickly show you what we did as part of the demonstration. So the online demonstration happened last year in May. We were able to demonstrate the technical integration of all the subsystems mentioned before. And during this live session, we had the opportunity, as the market conditions allowed us on that specific day, to do the autonomous, fully end-to-end control of the demo site in this VPP. And also what I want to mention is that, as we take the wind as it is, there's a requirement to deal with these short-term deviations, and all this is happening within the VPP controller. And the long-term optimization is happening in the VPP core. Next slide just shows a very brief a few screenshots from the different tools and how the integration looks like. The VPP tools, core and controller on the left-hand side, and on the right-hand side, the integration into Unsch, so the dispatch center of EDP, and on the bottom right, EDP Pro where we could really see a own balancing area, a virtual balancing area created for the VPP. And you could see the deviations or how the deviations being handled by the VPP controller on that particular screen. Thank you. Next slide. Also part of the work package and a demonstration was an offline demonstration, which is basically was done as a simulation of the performance of the VPP over 1 year. So we took the year 2016 to simulate across multiple scenarios the behavior of the demo site, both on if treated as individual units bidding into the markets and also when combined as a virtual power plant. What we were able to show is that the imbalances reduce significantly, and also that overall we see a slight increase in revenue when performing as a virtual power plant. The results have been presented in Tableau overviews. Okay, thank you. Next and last slide. So some key findings, just to sum up what we've seen. The pooling of volatile producers reduces relative forecast errors. That means basically if more renewables are part of the equation compared with controllable loads and generation, that makes the system even more stable and the behavior more forecastable. Pooling of producers and consumers reduces effects that come from the uncertainty in market price forecasts. Energy storage obviously helps to shift power production and consumption. It allows you to want to do price arbitrage on markets and also handle deviations from forecasts, both available power forecasts and energy market prices. A lever to really improve the overall performance of a VPP is what we see mostly around the forecasting. So more accurate forecasts of market prices, and a few algorithmic enhancements obviously will result in a better performance of the VPP in terms of imbalance reduction and in terms of revenue increase. And overall, the VPP is a very viable and practical tool to aggregate and jointly operate renewable energy sources units, both variable plus controllable. And the EU-SysFlex project was laying the foundations for a cross-dispatch link in a diversified portfolio like EDP has, combining hydro and variable renewable energy sources. Yeah, that's all from my presentation. Thank you.
Yep, sorry. Thank you very much, Michael Miguel. We'll move on to the last VPP, the Finnish demonstration, and that will be presented by Oliver. Oliver?
Hello, everybody. I'm Oliver Ojola from Helen, the Finnish demonstrator, and I'm going to present the market-based integration of these distributed resources in our transmission system. So next slide, please. The scope of the demonstration was to aggregate so far untapped small resources to the TSO and DSO needs. And we had several different sub-demos relating to the complete so-called VPP. We had active power units, which consisted of 3 different scale batteries, small scale, medium scale, and industrial scale, as well as electric vehicle charging controlling. In addition, we had for reactive power, we had the industrial scale battery and a PV plant inverters were used for that. Next scale, please. So the main part of a VPP or aggregation platform forms the foundation to control and optimize the assets. And in the Finnish demonstration, we had several different aggregation platforms for different assets. And we tried to find the best working solutions for aggregating these assets. In order to have the aggregation platform and the assets to be served for the markets, we of course then need to have the trading systems fully operated, which as an energy company we have for the for instance for the TSO's ancillary services. But the integrations between the trading systems and the aggregation platforms are of course very important. So we had the industrial scale battery was a 1.2 megawatt, 0.6 megawatt hour battery energy storage, which was connected to mid voltage, and it was controlled with a single aggregation platform. Then we had two different EV charging demonstrations. One which was controlled with a Virta energy platform, and then just a proof of concept, a different type of test via an IoT platform. And then we had the customer scale batteries, which was controlled with a different system approach, where we had this DES integration platform or aggregation platform, but that had required several integrations to a vendor cloud. And then we had the IoT platform, which showed the most potential for future asset controlling and optimization, where we attached the office scale battery and the PV power plant, as well as the pre-mentioned one test EV charger. Next slide, please. So I will go next through all of the different assets and the sub demos in the demonstration. So we had this industrial scale BESS, which was connected to the mid voltage grid, and during our research, we developed forecasting and optimization tools to estimate the availability of the flexibility to the TSO's ancillary service. And in the beginning of 2019, we began to offer the battery to the TSO's FCRN market, and ever since it has been successfully operated in the market. In our demonstration, we found out that especially these industrial scale batteries are a scalable solution for high-res grid, and things to consider when implementing these batteries is first, in the Finnish regulatory framework, we can get these grid scale or industrial scale batteries without power tax or energy tax, so that's something which reduces costs quite significantly. And also, if we find a location where we have rather low power tariffs, then the operation is, of course, we can get better profits out of it. So what has been studied that with the use of a industrial scale BESS, we can increase with this size battery 45,000 euros per year when we provide 0.5 megawatt to the FCRN market, and the profits after these power tariffs and so on is over 22,000 euros. And also it was quite good, the usability of the battery. It was almost 95%. However, there is of course a lot of improvements that could be done for the asset. Next slide, please. Then another battery, which was a medium scale battery or office scale battery. This was a 120 kilowatt, 136 kilowatt hour battery connected to low voltage grid in the office. For this battery, we successfully developed communication systems and control and optimization logics for the battery, which consisted of multi-use of the battery. Also, we needed to develop trading integration systems from the IoT platform to Helen's energy trading systems in order to operate in the FCRN market. And on the top rightmost figure, we can see how the different how the communication and bidding to the power market can be accomplished with this battery. So we successfully have operated this office scale battery also in the FCRN market, and other operations were local office building peak shaving. So because the office has a power tariff, then we can peak shave the power requirement of the office, and thus results in lower power tariff. Also, we demonstrated reactive power compensation. And on the middle figure, there is a 30-minute snapshot when the battery is operating in the FCRN market, and you can see that the battery follows very well the frequency change. The key results from this medium scale battery is that we found out that the IoT platform resulted in a very reliable way to aggregate this battery, and also this single battery showed that it was really very reliable and usable. But because this is quite a small battery, the increase in revenue was approximately 7,600 euros per year. Next slide, please. Then the third battery size we used was this residential scale or small scale batteries for the active power. We had 13 different customers who owned the batteries. They were from 1.5 kilowatt to 5.5 kilowatt, averaging the total power to approximately 3 kilowatts. There were some issues when trying to control these different assets because the batteries were controlled via a vendor cloud and through an integration platform from the aggregation platform. So there were quite many steps for controlling these different assets. And unfortunately, the tests we made with these, it showed that it was technically quite hard and did not fulfill the requirements related to the FCRN markets. Another aspect is that it's really not that economical for the customers to give their batteries for the use for frequency containment reserve. The thing is that mainly the batteries are purchased for optimizing power or energy usage with their own solar PV. So thus we could have used those batteries only for the winter time when low PV output is gained. Next slide, please. And then another active power was demonstration was using EV charging. We had in total 8 AC EV chargers, 22 kilowatt each, and one 50 kilowatt DC fast charger. We managed to successfully develop the control and control logics for controlling the charging stations. However, because we tried to provide the service from EV charging to the TSO's FCRD market, so to reduce the charging power, there is a strict 5-second time requirement that was not fully received. And also in 2019, we calculated that all of Helen's public chargers in average power was 70 kilowatt, peaking at 200, and that did not since fulfill also the 1 megawatt minimum bid to the FCRD market. However, if we calculate the increase in revenue or the potential, we could gain up to 3,000 euros with only that 70 kilowatt. So if we multiply that up to the megawatt, then of course we could get better revenue. Once the chargers had obtained the command for reducing the power, then it was fast, but the aggregation platform from getting the frequency and calculating how much power was required to reduce, that took longer than expected. And here is you can see on the bottom left the architecture which was used for the charging demonstration. And then on the right hand side we can see a snapshot of the DC charger reacting to the frequency change. Next slide, please. The last active power asset we used was trying to control electric heating loads via an automatic measurement controlling system. And these loads were, for example, water tanks, hot water tanks as energy storage that are already in the controlled with nighttime change to go on and off. And we made a simulation how these assets could be used in the MFRR market. Unfortunately, the technical tests could not meet the strict time requirements for this market, as the air meters are not designed for such use. And also here, as well as for the residential scale BESS, the estimated load for profitability was quite low. So the key outcomes for over 700 customers was that we could increase, of course, the revenue up to 56,000 euros, but per load it would stay quite low. Next slide, please. In addition to the active power, we had the reactive power market demonstration where we used two assets to provide service to the local DSO using the solar PV inverters 0.8 megawatt and the industrial scale BESS at 0.9 megawatt. As a technical proof of concept, we provided that this can be done to reduce the reactive power in the TSO-DSO connection point. And as key results, we found out that reactive power market utilization factor was 27%. And with these two assets, we found out that the decrease in possible penalties going out of the PQ window was -16%. And also these assets in the control were very usable and aggregated almost 100%. Next slide, please. So recommendations and future possibilities in other than what has been already presented. I want to underline that an agile and reliable aggregation platform is the key to promoting replicability and scalability. Also, forecasting and optimization of the assets is further to be developed for successful market operations. Other recommendations is that all technologies are to be treated in a natural way for the future power system, as well as the rules for the ancillary markets to be developed to allow these smaller units for different type or of control. Then another aspect is the acceptance of the end user if they own the flexibility assets, so that we as an aggregator can fully take advantage of them and identify and support them. So also, in addition to the active power, we also promote that the reactive power assets could be used for future needed. And also for the BESS, it is strongly advised to use them in different type of operations. Another thing for the EVs is that in the future, as more and more EVs are on the road and power demand for charging them, this can provide a major role in the future or major possibility. Next slide, please. Just a quick recap. So we have these different assets, and the main objective was to aggregate these small distributed assets to the TSOs and DSOs needs. Thank you very much.
Thank you so much, Oliver. We'll move directly to the last presentation, which is the one from John Wallace, and to give us an insight in 5 minutes on the QTPs that were held in Ireland and Northern Ireland. John?
Thanks, Marianne. So yeah, my name is John Wallace. I'm a senior lead engineer here in the innovation and research team at EirGrid. And within the context of EU-SysFlex, I was the work package 4 lead. So work package 4 was titled Simulation of the Integration of New System Services into System Operator Control Centers. And one of the key objectives within this work package was an implementation of a qualifier trial process, which I'm going to present on very briefly. So next slide, please. So the image on the left here illustrates the need for new system services and operator tools to overcome the technical scarcities and challenges which are highlighted in Work Package 2 of EU-SysFlex, to enable the secure and reliable operation of the future power system. So the qualifier trial process effectively carries out the proof of service provision block within this image, and it provides a gateway for new technology classes to demonstrate their ability to provide the system services that are needed and meet the criteria laid out by the system operator. So this platform has supported the ER system in reaching 70% instantaneous non-synchronous penetration levels, with 75% being trialed, and the medium-term target being in excess of 90% by 2030 to meet our RESI goals. So next slide, please. Thank you. So there are a number of key principles considered in the operation of these trials. So the trials are run at a scale which mitigated risk on the wider system, but enabled meaningful analysis and results. Real system conditions and operation were used in order to demonstrate the veracity of this provision of the system services in practice. The service provision was considered on a technology class basis rather than on a service provider basis. Participant failure was viewed as a learning for a potential future trial, rather than necessarily being a permanent exclusion. So the qualifier trial process was carried out over 3 phases throughout the EU-SysFlex. A number of technology classes were investigated, such as wind and solar, aggregated residential service provision, alternative communication methods, and TSO nodal controller for the optimization of distributed gen power factors, amongst others. And the types of system services being trialed included fast frequency response, primary, secondary, and tertiary operating reserve, dynamic reactive response, and fast post-fault active power recovery. Next slide. So throughout the project, there was an array of trial technology classes across 3 phases, which ended up demonstrating service provision successfully. Those were considered as proven, which enabled them to be added to the EirGrid DS3 System Service Proven Technologies list, which can be found on our website. For others, barriers and learnings were identified for future trials, and reporting across the 3 phases are documented on the EU-SysFlex website. Another key element was the FlexTech initiative. So this was a forum which provided the platform for stakeholder engagement across TSOs, DSOs, industry and regulators for identifying opportunities and removing barriers to renewable integration. And that proved vital to the success of recent phases of QTP. And really the overall takeaway is that as system reliance on non-synchronous variable res generation increases, we do need these new services and technologies to maintain the reliable and secure operation of the system. And here in Ireland, we found the qualifier trial process provided the platform needed to prove and demonstrate service provision from these new technologies. So that very quickly covers my material. So thank you. Back to you, Marianne.
Thank you very much, John. So next slide, because I think we've taken the questions in the chat. It was easier because we're a bit late in the webinar. So just first, I would like to really thank all our speakers and all our partners that were involved in these very comprehensive and interesting and needed demonstrations to make sure that we'll be able to deliver the future power system with low carbon energy and still reliable and efficient. So in conclusion, I will go in 5 minutes, recap a bit what we did. And it's not easy to try and recap in a few minutes the very comprehensive work that was done for 4 years and 4 months. So thank you very much for the work in the demonstrations. It was very important work, very extensive work. All this work supports 3 of the key messages of the project. So the first one, I will just read through those three main messages. So the first one is about the fact that we need new operating tools. So as we've seen, many of the tools that were delivered and developed in the demonstrations, and what they show is that new decision support, new operating decision support tools are needed for the future power system if we want to be able to access and activate the needed flexibilities, with in particular enhanced forecasting, state estimation, and optimization capabilities. So that's the first key message that is supported by the main findings of the demonstrations. Next slide, please. The second one is, of course, about the TSO and the key critical needs that we have to enhance TSO-DSO coordination. So this efficient coordination between transmission system operators and distribution system operators is really critical, given the significant share of future resources, not only generation, but also all flexibility assets that are connecting and will continue to connect to the distribution network. So this is a key outcome of the project. And third key message that is supported, so next slide, please, by the work in the demonstration is the one about the value of aggregating and the aggregation of decentralized resources. Because as you have seen in the presentations, we have many more and smaller resources connecting to various levels, voltage levels of the system. And aggregation of these decentralized resources will enable access to a wider range of flexibility options, and including the participation, although we've seen that we still have some challenges, but of residential customers and a range of distribution connected aspects. So next slide, please. I just want to remind, I will not present again those 8 key messages, but the demonstration work supported in particular those 3 key messages, but there are also 5 others and important messages if we want to make this future system happen. And they relate, and we've heard it mentioned in most of the presentation: market enhancements, regulatory changes, and also to tackle quite a few challenges in terms, quite a lot of challenges in terms of ICT as well. And finally, so the roadmap is being finalized. So, next slide, please. The roadmap is now being finalized, and you can find with this roadmap, this document that will be published very soon on our website, fact sheets about all the demonstrations that were part of this project. And so if you want to have access to all the key outcomes that were summarized today in this webinar, you can find them in the fact sheets of the demonstrations that are part of the flexibility roadmap of the EU-SysFlex project. And I think this is my last slide, just the final one. Next. Hello. So just so that you see at the bottom and here on the right-hand side of the slides, you can find all of our complete results. So not only fact sheets and summaries, but all our complete results are public, and you can find them available on our websites. We've had many webinars, technical webinars like this one, and they have all been recorded, and you can find also the replays, the recordings on the website. So thank you for attending this webinar. Thanks again to all the speakers and our partners in the project. And if you have any questions, you can always send them to us through our social media. Thank you very much, everyone.